Hello dear learners, a very warm welcome to all of you. Today we embark on an in-depth exploration of ethics in engineering with a particular focus on integrating ethical principles into technology and professional practice. This lecture is designed to guide you through the philosophical foundations, practical relevance, and professional implications of ethics in engineering, while encouraging you to reflect on your own role as responsible technologists in a rapidly evolving world. Before we begin the discussion, let me briefly outline the objectives of this lecture so that you have a clear sense of direction. By the end of this session, you will be able to understand the conceptual foundations and philosophical origins of engineering ethics, analyze the structural principles and rational processes that guide ethical reasoning, examine the relevance of ethics across personal, social, and professional spheres, understand how ethical principles are integrated into professional practice and behavior, and recognize the importance of accountability and responsibility in shaping the professional identity of an engineer. With these objectives clearly in mind, let us now begin our discussion. Dear students, engineering at its core is the disciplined application of scientific knowledge, mathematical principles, and technical skills to design, build, and maintain systems, structures, and technologies that address human needs and societal challenges. It's a problem-solving profession aimed at improving quality of life through innovation, efficiency, and reliability. However, because engineering solutions directly influence public safety, environmental sustainability, and social well-being, the practice of engineering extends beyond technical competence and enters the realm of moral responsibility. Engineering is often perceived as a discipline defined by mathematical precision, scientific reasoning, and technological innovation. However, beneath every design, system, and solution lies a silent yet powerful framework of ethical responsibility. Engineering ethics is a specialized domain of applied ethics that establishes the normative standards governing the conduct of engineers in their technical, social, and environmental capacities. It reminds us that engineering is not value neutral. Every technological decision carries moral implications that affect individuals, communities, and ecosystems. Engineering ethics is not a reactive mechanism reserved solely for moments of systematic failure or industrial crisis. Rather, it's a proactive and continuous determinant of professional agency. It informs the smallest design decisions, the largest project management strategies, and the overreaching commitments engineers make to public welfare. Whether one is engaged in structural design, software development, or environmental remediation, ethical considerations dictate professional behavior and define the relationship between the technologists and the global community. Historically, the progress and stability of societies have relied upon shared values such as integrity, distributive justice, honesty, and social responsibility. In the contemporary technological landscape, these values are synthesized into professional codes of ethics that emphasize safety, sustainability, and transparency. This lecture does not treat ethics as an isolated academic abstraction. Instead, it seeks to promote the internalization of ethical imperatives so that they may be applied with rigor in personal life, social interactions, and professional practice. The ultimate goal of engineering ethics education is the development of conscious ethical agency. This involves transitioning from an initiative or unconscious moral stance to a state of reflective ethical awareness. Ethics in engineering is a lived praxis expressed daily in the selection of materials, the assessment of risk, the reporting of data, and the stewardship of resources. By cultivating analytical reasoning and reflective judgment, engineers learn to navigate the complexities of modern practice, where technical capacity must always be moderated by moral obligation. Let us now turn to the first objective of this lecture, which is understanding the conceptual foundation of engineering ethics. Ethics at its core is the systematic study of the normative principles that govern human conduct and decision making. While philosophy broadly examines questions related to existence and knowledge, ethics or moral philosophy focuses on evaluating human actions. It distinguishes right from wrong, justice from injustice, and virtue from professional negligence. In engineering, ethics provides the evaluative framework through which decisions with real-world consequences are assessed. The critical distinction exists between technical competence and ethical discernment. Technical knowledge expands what engineers are capable of achieving by equipping them with the skills to design complex systems, optimize performance, and push the boundaries of innovation. Ethics, however, determines what engineers ought to achieve by providing the moral framework within which technical capabilities must operate. In an era of rapid scientific and technological advancement, where innovations can have far-reaching and irreversible consequences, this distinction becomes especially significant. Knowledge informs engineers of what is possible, but ethics mandates responsibility, restraint, and accountability in the pursuit of those possibilities. Ethics serves as the architect of professional conscience, guiding engineers towards actions that are not only technically feasible but also morally permissible, publicly defensible, and socially responsible. For example, an engineer may possess the technical expertise to deploy a cost-effective material or algorithm that maximizes efficiency, but ethical discernment requires evaluating whether that choice compromises user safety, data privacy, or environmental sustainability. In such cases, ethical judgment ensures that innovation is aligned with human values, reinforcing the principle that professional excellence in engineering is defined not solely by technical success, but by responsible and conscientious decision making. Ethical values function as an internalized system that directs human agency. Within the engineering paradigm, these values manifest as honesty, transparency, empathy, and accountability. Ethics enables engineers to move beyond mere compliance with external rules towards autonomous moral reasoning, where competing duties, social consequences, and professional responsibilities are carefully weighed. Ethical thought emerges from multiple sources. Philosophical reflection provides rational frameworks such as utilitarianism, and deontology, which offer systematic methods for evaluating moral claims. Cultural and social traditions contribute inherited values that promote communal harmony and collective welfare. Professional socialization shapes ethical understanding through lived experience within engineering communities. While expressions of ethics may vary across cultures, the ultimate goal remains universal: fostering trust, justice, and the minimization of harm. Now we move on to the second objective, which focuses on understanding the structural principles and rational foundations of ethical reasoning. Engineering ethics is fundamentally normative and prescriptive in nature, meaning that it is concerned not merely with observing or describing how engineers behave, but with establishing clear standards for how they ought to behave. Unlike descriptive approaches, which record existing professional practices without evaluating their moral quality, normative ethics defines the principles and obligations that should guide engineering conduct. It asserts that certain core values, most notably public safety, honesty, accountability, and responsibility, are morally binding and must be upheld regardless of economic pressure, organizational hierarchy, or institutional convenience. As a prescriptive discipline, engineering ethics offers concrete guidance for action, enabling engineers to make principled decisions in complex situations where technical efficiency or profit may conflict with moral duty. It also functions as a corrective force when professional ideals are threatened, reminding practitioners of their primary obligations to society and the environment. For example, if an engineer is instructed to overlook safety test failures in order to meet project deadlines or reduce costs, normative ethical principles require the engineer to prioritize public safety over compliance with managerial demands. In such situations, ethics does not merely describe the dilemma, but clearly prescribes the morally appropriate course of action, reinforcing the engineer's responsibility to protect human life and uphold professional integrity. Ethical practice in engineering is grounded in universal values. Principles such as justice, honesty, and respect for human life transcend cultural and geographical boundaries. These shared values make it possible to establish international safety standards, environmental regulations, and professional codes of conduct. While local conditions and project requirements may differ, the fundamental moral obligation to protect people and the environment remains constant. Ethics is also concerned with human agency and intentionality. Ethical evaluation considers not only technical outcomes of engineering projects, but also the motivations behind decisions. It asks why certain choices are made and whether they reflect a sincere commitment to public welfare or are driven primarily by profit or personal advancement. This focus on intention ensures that technical expertise is exercised with moral purpose. A defining characteristic of engineering ethics is its rational and logical foundation. Ethical decision-making is not based on intuition or emotion alone. It's a structured cognitive process known as moral reasoning. Engineers must systematically analyze duties, rights, risks, and consequences. This rational approach allows ethical decisions to be defended with the same rigor applied to technical analysis. Ethics also plays a vital role in promoting social cohesion and institutional trust. The engineering profession operates under a social contract with the public. Ethical behavior maintains this trust by ensuring transparency, accountability, and safety. When ethics is neglected, technological failures and exploitative practices erode public confidence and destabilize social systems. Ethics is dynamic and evolutionary, reflecting the continuous moral development of society as scientific knowledge, technological capability, and social awareness advance over time. As new technologies such as artificial intelligence, autonomous systems, nanotechnology, and large-scale data analytics emerge, they introduce unprecedented capabilities as well as novel ethical risks and dilemmas that were previously unimaginable. In response, ethical standards must evolve to address issues such as algorithmic bias, loss of human oversight, environmental uncertainty, and threats to privacy and human dignity. Practices that were once widely accepted may later be judged unethical as societal understanding of environmental stewardship, sustainability, and human rights deepens. For example, the unrestricted collection and use of personal data was once considered a normal aspect of technological progress. But today, it raises serious ethical concerns related to consent, surveillance, and discrimination. Similarly, industrial practices that prioritized efficiency over environmental impact were historically tolerated, yet are now ethically challenged due to increased awareness of climate change and ecological degradation. These shifts demonstrate that engineering ethics is not static or fixed, but an adaptive framework that must continually respond to evolving technologies and societal values to ensure that innovation remains aligned with human welfare and moral responsibility. Let us now turn to the third objective, which is examining the multidimensional relevance of ethics. Ethics operates across three interconnected spheres of human existence: the personal, the social, and the professional. In the personal sphere, ethics cultivates self-discipline, sincerity, and an internal moral compass that guides behavior even in the absence of external oversight. In the social spheres, ethics promotes cooperation, mutual respect, and equity, ensuring that technological progress does not undermine social justice. In the professional sphere, ethics ensures accountability, transparency, and the prioritization of public safety over individual or corporate gain. In the intrapersonal dimension, ethics strengthens moral agency and professional character. Engineers frequently make critical decisions privately, such as reporting calculation errors, admitting design limitations, or refusing to compromise standards. An internalized ethical compass ensures that these private actions align with public responsibility. This personal accountability is a primary defense against negligence and professional misconduct. In the interpersonal and socio-political dimension, ethics functions as the connective tissue that holds technological societies together. By emphasizing fairness, honesty, and respect, ethical engineers protect vulnerable populations and promote distributive justice. Ethical practice requires evaluating whether the benefits and burdens of technological progress are distributed equitably and ensuring that marginalized communities are not disproportionately harmed. In the professional sphere, ethics establishes credibility and ethical leadership. Professional ethics define the duties engineers owe to clients, employers, the public, and the profession itself. Ethical leadership fosters organizational cultures that prioritize safety and integrity over short-term financial gain. In doing so, ethics ensures that engineering remains a respected vocation rather than merely a technical trade. The fourth objective focuses on integrating ethical principles into professional practice and behavior. Ethical principles form the foundation of engineering decision-making by providing a moral framework that guides professional judgment beyond technical calculations and efficiency metrics. Respect for autonomy emphasizes the inherent dignity of individuals and the importance of informed consent, requiring engineers to ensure that users and affected communities are adequately informed about the risks, limitations, and impacts of technological systems. Beneficence obligates engineers to actively promote public welfare by designing technologies that enhance safety, accessibility, sustainability, and quality of life. Non-maleficence reinforces the paramount importance of avoiding harm, compelling engineers to anticipate potential risks that implement safeguards that prevent physical, psychological, or environmental damage. Justice demands fairness and equity in the distribution of technological benefits and burdens, ensuring that marginalized or vulnerable populations are not disproportionately exposed to risks or denied access to essential infrastructure. Integrity unifies these principles by requiring honesty, transparency, and moral courage, particularly when engineers face pressure to conceal errors, manipulate data, or compromise standards. These ethical principles are translated into professional practice through established codes of conduct, systematic risk management frameworks, and reflective decision-making processes that encourage accountability and foresight. They guide engineers in complex situations where technical data alone cannot determine the correct course of action, such as when multiple design options meet performance requirements but differ significantly in their social or environmental impact. For example, when developing a new transportation system, an engineer must balance efficiency and cost with safety, environmental sustainability, and equitable access for all users. Similarly, in software and artificial intelligence development, engineers must consider user privacy, data security, and potential bias alongside functional performance. By consistently integrating ethical principles into daily practice, engineers align technical excellence with moral responsibility, ensuring that innovation serves the broader interests of society while maintaining public trust and professional integrity. The final objective concerns accountability in professional formation. Ethics plays a central role in shaping the professional identity of engineers by emphasizing responsibility towards multiple stakeholders, including clients, employers, society at large, and the natural environment. It reinforces the understanding that engineering decisions carry far-reaching consequences that extend beyond technical performance and economic efficiency. Accountability ensures that professional success is measured not only by innovation, productivity, or cost effectiveness, but also by adherence to ethical standards such as transparency, safety, sustainability, and social justice. An engineer's credibility and professional reputation are therefore grounded in the consistent demonstration of ethical conduct, particularly in situations where commercial interests or organizational pressures may conflict with public welfare. Education plays a crucial role in cultivating this ethical identity by embedding ethical reasoning within engineering curricula, rather than treating it as a peripheral subject. Through the use of case studies involving real-world engineering failures and successes, students learn to analyze complex moral dilemmas where technical solutions alone are insufficient. Experiential learning opportunities such as community-based projects or sustainability initiatives allow learners to directly observe the social and environmental impact of engineering decisions. Role modeling by educators further reinforces ethical values as students internalize professional norms by observing integrity, fairness, and accountability in academic practice. Reflective assessments, including ethical journals and scenario-based evaluations, encourage learners to critically examine their own values and decision-making processes. Ethical education thus bridges the gap between theory and professional practice by transforming abstract principles into practical judgment skills. It prepares engineers to navigate moral dilemmas with confidence, clarity, and moral courage, whether they are reporting safety concerns, managing conflicts of interest, or designing technologies with long-term societal impact. Through continuous reflection and active engagement, learners internalize the understanding that ethical responsibility is inseparable from professional competence, ensuring that engineering excellence is defined not only by what can be built, but by what ought to be built in service of humanity and the environment. In conclusion, ethics constitutes the indispensable normative foundation that sustains professional integrity and social trust in engineering. It guides innovation, moderates technological power, and ensures that progress serves humanity rather than undermines it. When ethics becomes a lived practice reflected in honesty, fairness, accountability, and respect, engineering fulfills its highest purpose. Dear learners, let ethics become a way of life that we live and practice every day. Thank you for your attentive listening.